Okay, let's look at one more torque problem. This one would be as hard as it gets. We call this a level 3 torque problem simply because the beam itself is at an angle. So you're going to have to deal with a lot of sines and cosines to try and figure out what the perpendicular forces are. But once again, we're going to start the same way that we always start. The question asks, what is the tension in this rope, this horizontal rope that's keeping the beam from falling? There's a hinge at the base about which the beam is rotating. The angle that the beam is resting at is 40 degrees with the vertical. The rope is attached at the 2-meter mark along the beam, and at the end of the beam, which is 3 meters long, is a 15-kilogram weight. Now the beam itself has a mass of 10 kilograms, and we already know that that mass will be concentrated, or that force of gravity will be concentrated right at the dead center of the beam. So once again, I'm going to simplify the diagram and label just the forces acting on the beam. Let's start with the force acting at the end of the beam, which is produced by this mass, or this weight, and we'll call that Fw. The next force we're going to worry about is the weight of the beam itself. We're going to call that Fb for F-beam, and we know it acts right at the dead center of the beam. And then the last obvious force is the tension force on the rope, which we know acts at a horizontal, and it is at the 2-meter mark, which is roughly there on my new diagram. So there's the three obvious forces. Now, just like the last question, we have to recognize that the hinge itself is undergoing some forces. There's a horizontal force acting to the right, kind of like a normal force, and that has to oppose this tension force on the rope. There's also an upward force keeping this bottom part of the hinge, keeping the beam from slipping down the wall. And that upward force, if all the forces are to be balanced, which they are because this beam is not moving, would have to be equivalent to Fb plus Fw. So we're going to label those just like we did in the last problem as Fx and Fy. Now, as we've seen in the last problem, these questions can get complicated quite quickly. So let's try and simplify this as much as we can with some numbers. We can calculate Fw, the weight of the beam, fairly easily. Fw is simply 15 times 9.8. Let's put that in instead of Fw. So with a quick calculation, 15 times 9.8 gives 147 newtons straight down. Similarly, the weight of the beam, which acts right in the dead center of the beam, if the beam weighs 10 kilograms, 10 times 9.8 is 98 newtons. Let's replace Fb with 98 newtons. Now, once again, we know that torque comes into play here because we've got a long object and forces are acting at various locations along that long object, causing it to rotate about a hinge, or trying to get it to rotate about a hinge. The 98 Newton force and the 147 Newton force, if my hinge is my pivot point, are trying to cause it to rotate clockwise, and Ft is preventing it from rotating clockwise by creating a counterclockwise torque. Now, with torques, we need the force and the distance to be 90 degrees. That's the key. So if I look at my diagram, they've provided the distances for me. They're along the length of the beam. I've got a 2-meter distance along the length of the beam where the rope is attached, and the length of the beam itself is 3 meters. Now, if we're going to use these distances, these lengths along the beam, the 2-meter, the 3-meter, and of course the halfway point of the beam would be 1.5 meters, we need forces to be perpendicular to those distances. Right now, if you look at my simplified diagram, my distances are along the beam. So here's 2 meters to where the tension force is, but clearly my tension is not 90 degrees to that distance. So we're going to relabel our diagram and calculate what those perpendicular forces are if possible. Now, sometimes the geometry can trip us up a little bit. We only know the one angle, it's given at 40 degrees, but you see a lot of 90s and a lot of right triangles in this question. So let's put in as many angles into my simplified diagram as possible. So if we start by labeling my 40-degree angle, and that's with the vertical, clearly Fy and Fx would have to be at 90 degrees as they're orthogonal. This little angle right in here would have to be 50 degrees. Now, if I look at my original sketch, I see a triangle on the inside here where the rope, the wall, and the beam make a right triangle. So if that's 40 degrees and that's 90, I get 50 degrees right here. Let's put that in. Now, the next step we want to do is rewrite our vectors as components that are perpendicular to the beam. So the 98 and the 147, we want to find the component that's at 90 degrees to the beam. Keep in mind that the original vector is always the hypotenuse when you're trying to figure out components. So I'm going to label those with dotted lines. We're going to show what the components are. The one parallel to the beam and the one perpendicular to the beam, and obviously we're focusing on the perpendicular one. Let's do that now. Okay, here we see our components nicely labeled. The red ones are all perpendicular to the beam, and these really thin black ones that are hard to see for a reason because we're not really interested in the ones that are parallel to the beam. Those of course are our parallel components. Now let's get some more angles. First of all, we have a series of 90 degrees in here. Perpendicular to the beam literally means 90 degrees to the beam. Let's label that. Okay, so I've labeled the 90s. There's a 90 right here with this red component, the perpendicular component, and a 90 right here. This is going to allow us to figure out the last of our angles. So if I've got 50 degrees here and fx and the 98 make another 90, there's going to be 40 degrees right in there, which is going to give us back 50 degrees right here, because don't forget this red dotted line is 90 degrees to the beam. So let's label 50 degrees here and similarly 50 degrees up here. Now it's starting to get quite complicated, so I'm going to try once again to simplify my diagram. All I really need are these perpendicular components to figure out some torques. I'm going to use the bottom part as my pivot point, which is usually the natural location anyway because that's the hinge. Once again, I picked this as my best location for my pivot point because the torques generated by Fy and Fx, which are basically unknown, we could calculate them, but they're unknown for now. If I use that as my pivot point, the distance to that pivot point, which is how you calculate torques, is 0 for both Fy and Fx. So they're not contributing to any rotation if that's my hinge. So my pivot point is going to be at the bottom. Fx and Fy are not going to come into play in my torque equation. So I need to figure out these dotted lines in here. If I know the hypotenuse is 147 and I know the angle is 50 degrees, this side here would be the adjacent side for both of these triangles. So what I can do is use the cosine. Cosine 50 is adjacent, which is what we're looking for, over hypotenuse. I'll solve one and then we'll simply simplify the diagram. We see my equation on the lower left. Cos of 50 degrees is adjacent over hypotenuse. My adjacent I'm labeling F perpendicular. That's going to be this little dotted line right here. And the hypotenuse of that triangle is always the original vector, 147 newtons. And when I work it out for F perpendicular, I get 94.5. So this little piece right here is 94.5 newtons. Okay, so we have 94.5 newtons already labeled on the diagram. We could do the same thing for the 98 newton force and just go 98 cos 50, and that gives us 63 newtons. But again, I want to try and simplify it. So what I'm going to do is erase everything except for our solved perpendicular component so that we can see an easier sketch and solve this more simply. So here we see my simplified sketch. I've got two forces that are producing clockwise torques. Notice I've gotten rid of Fx and Fy just to avoid any clutter and avoid any confusion. I'm going to call this my pivot point, so all my distances have to be from that point. And fortunately the diagram gives us those values, so it's going to be easy. Acting at the 1.5 meter mark is the weight of the beam. Remember, the entire beam is 3 meters long, so halfway is where the weight is, and that'll be at the 1.5 meter mark. So 63 newtons acts at 1.5 meters. Similarly, the 94.5 newton force acts at the end of the beam, and we're concerned about distances from my chosen pivot, so its distance is going to be 3 meters away. The last distance we need to concern ourselves with is the distance where the tension acts. And according to our diagram, it's 2 meters away from my chosen pivot point. So we'll label that one as well. So we see my simplified sketch. I have distances and forces that are acting at 90 degrees to each other, so we can start to calculate torques about our pivot. The 63 and the 94.5 newton forces are creating clockwise torques, and they have to be balanced by this tension force creating a counterclockwise torque. So we can set up our equation in a slightly different way if we like. Instead of saying that the sum of the torques equals 0, we can say that the sum of the torques clockwise equals the sum of the torques counterclockwise. So there's lots of ways to write this. I choose to write it as sum of the torques, and I made an arrow in the clockwise direction. So sum of the torques clockwise have to be balanced by the sum of all the torques counterclockwise. I'll have 2 clockwise torques, and that has to be equal to the 1 counterclockwise torque. Now it's just a matter of the equation. We know that torque is force times distance. So torque is force times distance, where the force has to be perpendicular. So let's fill in our values. I've got a 63 Newton force acting at 1.5 meters. So the first torque will be 63.0 newtons force times distance of 1.5 meters. That's my first clockwise torque, plus my 94.5 Newton force acting at 3 meters. Has to equal, well, what does it have to equal? It has to equal the torque produced by my tension force. Now I can't simply say it's Ft times 2 because Ft is not perpendicular to this 2 meter distance. So it's going to be this dotted line here. Now you can call it whatever you like. Let's just call it F perpendicular for now. That's what we're going to try and solve for. So we'll look for F perpendicular times 2. So when I do this and solve for F perpendicular, I get 189 newtons. So the side of this triangle right here is 189 newtons. So now it's just a simple matter of some trigonometry to solve for the hypotenuse. This side is opposite to our angle, and we're looking for the hypotenuse. And opposite over hypotenuse is sine. So if I set up a quick equation using the sine, I would say sine of 50 degrees is opposite, which is 189, that was our calculated value, divided by Ft. And when I work this out, I finally get my answer to be Ft is equivalent to 247 newtons. So there's my answer.